Hello, everybody. Our conversation today is going to be about the role of the Greek letter phi when we work our solution. So, one of the rules of a second order differential equation of any function f is that the solution of f needs to have two variables that are left undefined until they are applied to a specific system. So two parameters, actually, undefined, until applied. Okay, so let's take that into the concrete, which is we found that x of t was equal to x max sine of an omega t when omega was equal to k over m. K over m is defined. X max is a parameter, how far you pull the spring system back. What is left undefined then is the Greek letter phi. So we're trying to define what phi means in a practical sense. So let's go graphical first. So a sine graph does this. The sine graph assumes that x at time t equals 0 seconds is equal to 0. So let me show you what I mean by that assumption. X at t equals 0 is equal to x max sine of our, this is amplitude, this is time. So sine of our time equaling 0 would just have us go omega times 0 seconds. Hold off on phi for just a moment. And we wind up with omega times 0 seconds is equal to 0 radians, technically. The sine of 0 is 0. So that brings this entire side of the equation equal to 0 at time t equals 0. But that may not be the case. We can imagine a case where, well, the easiest case is, what if I start high Oops, I screwed that little bit, that end up, so let me get rid of it. If we do a cosine function, it's 0. It goes to 0 when that's a maximum. When sine is equal to 0, it's a minimum. When sine's at a maximum, it's a 0. When sine goes to 0, it's a maximum, and so forth. So let me just write this as cosine. Of something as a function of time. And the blue here was our sine function. So it's easy to imagine then that we could have any starting position between sine and cosine. And that's where where phi comes in, because phi deals with something called phase, which is simply the starting position. So let's do an example of this mathematically. Okay, that was overkill, but I had fun drawing it. Let's say that we're given the situation that, still in the crayon mode, that let's try that again, where we have x at time t equals 0 is equal to, let's do this in terms of x max divided by 3. Then what we typically do, and you'll typically get, is the velocity as a function of time. At t equals 0 will give you a specific value. So let's assume that it's going at got the 1/3, so let's keep away from the 3's, and let's make this 0.7 meters per second. So this is where we can figure out what phi is equal to. We start with x, and our x solution for any value of time is equal to x max sine omega t plus phi. But if we're setting the time equal to 0, then this term drops out, and we can do the next step of the derivation, which is x at time t equals 0 is x max over 3. That equals x max, not to be confused with Christmas, sine of phi. So x max goes away, and we need to solve for sine of phi when it equals 1/3. So we get a phi equal to the, oops, make sure I'm in radians first. I am not. So take this moment and get yourself over to radians in your calculator. And we're going to do the inverse sine of 1/3. Close it up. And we get phi equals to darn near 0.4. So 0.34 is our value of phi. We're not done yet because we don't know what x max is equal to. That's our other parameter. And we can get that from the velocity. Because the velocity function is x max omega cosine omega t plus phi. All right, so let's make the substitution of 0.7 meters per second for velocity at time t equals 0. That'll give me x max omega and cosine of phi. Now, I said before omega was not a parameter. It had to be given to you. So let's set omega equal to 37. We haven't done anything with 5s yet, so how about 15? 1/seconds. Okay. So now, because we're looking for x max, it's again a straightforward calculation. We take the 0.7 meters per second, and we're going to divide it by omega, which comes in as 1/seconds. And then, oops, we actually know omega, my bad. It's omega. And then the cosine of 0.34. Okay. So calculator time. Let's take the cosine of that value. Okay. Times 15 divided by 0.7. Flip it. And I get x max for the system being equal to 0.0495 meters. Notice in above that the 1/seconds is going to cancel the 1/seconds unit-wise, leaving us just with meters for x max. So, with much fanfare, like a Beyonce release, we can get ourselves to a final answer, a final description of motion in this case, which says x at any moment of time is going to equal 0.0495 meters sine of our omega t plus our phase 0.34. And this is the final answer that describes the system we set up with these equations. So it's only valid for this exact set of equations with that omega, with that velocity at that time equals 0, and that value for x max. So that's our final answer.